what I want to think about in this talk really is the question of how we take account of the multiple trade-offs between different ways of managing the Earth's carbon cycle. Importantly, we have to remember, I think, and this is maybe the main point I want to make, that developing portfolios of mitigation strategies is a multi-dimensional problem, and it's not simply about the greenhouse gases. So just to illustrate some of the sort of dimensions of this problem here, it includes, for example, also food security, economics, biodiversity, health, pollution, political and social issues, waste, and resources demand, for example, for water and other critical resources. And deciding on how to manage the carbon cycle is really a case of balancing all of these considerations in light of the fact that many of these are going to be themselves constrained and affected by climate change if we fail to adopt the best available practices. So just to think for a moment about, before we look at all these trade-offs in different dimensions, just to think quickly about how this might look if we thought only about the carbon side. So this chart here shows the carbon abatement over 100 years per unit mass of carbon invested for a range of options for using biomass. And strikingly, we can see a very low carbon efficiency for soil organic carbon. That's SOC on the label there. And that's because the vast majority of any carbon that we add to soils, if we wish to increase the soil organic carbon stocks, ends up back in the atmosphere through respiration. If, on the other hand, we are to convert some of that biomass to biochar through pyrolysis, we lose around half of the original carbon during the thermochemical conversion. But the remaining biochar carbon is much more persistent than the biomass from which it derives. So we end up with a much more efficient system overall. Slightly better on average than the abatement we would get if we actually converted that same biomass to just pure bioenergy without BECCS. And if we recover some of the energy in the syngas during the pyrolysis and in biochar production, we increase the efficiency of the biochar system by around another quarter. But still, at this stage, it's only around half the carbon efficiency that we would get from BECCS for the same investment of biomass into the system. It may be possible to increase the efficiency of a biochar system slightly beyond that if we also include a carbon capture and storage and CO2 sequestration back end onto the thermochemical conversion pyrolysis part. But that's really an unproven technology that's quite speculative. Just to point out that even if we do that, we still don't reach up to the levels of abatement that we get per unit biomass carbon that we do get from BECCS. So with that in mind, why would anyone be interested in, for example, adding carbon into soils, which there's a massive growing interest in at the moment? And the storyline typically revolves around a few different aspects. One is that soil organic carbon contains about 3 times more carbon than the atmosphere, and that we've got a massive exchange naturally between the soil and the carbon in the soil and the atmosphere, with around 8 times as much CO2 exchange annually between soil and atmosphere than total anthropogenic emissions. Another aspect of this is the fact that soil organic carbon storage is seen to be quite scalable and affordable, that it requires a change in agricultural management across the nearly 3 gigahectares of agricultural land that we have already on the planet. So it's seen maybe as a low-hanging fruit of something that could be more easily implemented in some of the more technological solutions. So another side to the story is the co-benefits of soil carbon. This is a big part of the question. So here we've got a couple of graphs which are from a manuscript in preparation at the moment. So it's long been argued and suspected that soil organic carbon has a beneficial impact on crop yields, but it's been very hard to actually prove that quantitatively up to now, because there are a lot of sort of interactions with both the fact that increasing yields implies that you've got better crop growth, which implies more residues going into the soil, so you can have causality going in either direction. The crop yield increases could be driving the soil organic carbon. And there is such large number of covariates, both environmental and management, that go into it, that drawing out a sort of causal relationship has been very difficult. What we've got here is some data from a very large trial of around 70,000 controlled on-farm field trials in maize, wheat and rice across all cropping systems in China, with a large number of agricultural zones, which allow us to unequivocally show that if you've got more soil organic carbon up to a threshold, you will get better crop yields. So this is also another big part of the story that's often argued that it's beneficial to agriculture to increase your soil organic carbon. And a third angle to it is that soil degradation is a massive issue for large areas of the world, that we've got large areas of land, agricultural land, abandoned each year through soil degradation because the land becomes no longer viable for productive purposes. We've got over 1 billion people dependent on land that's already highly degraded. 20% of the Earth's vegetated land surface showing persistent trends in degradation. And of course, soil organic carbon and soil organic matter is a prime indicator of soil health. And if you remove soil carbon, you will drive land degradation. And one of the primary ways that we have of actually trying to address land degradation and soil loss is by actually increasing soil carbon stocks. And the final part of the picture of why people are interested in soil, of course, is that there are a number of other co-benefits from them, including, for example, I think importantly, things like water pollution. So in the northeast of the US where I am, in fact, one of the main drivers behind incentives to try and increase things like cover cropping, which do increase soil organic carbon, is not the carbon story, but the fact that these practices can help to mitigate runoff of nitrates and phosphorus and other sort of eutrophication into inland waterways and the water problems that go along with it. So these other sort of co-benefits of managing soils in a sustainable manner are often some of the main policy drivers at the moment. So what is the potential globally for actually using soil organic carbon sequestration to offset climate change? And this is the results from a recent study using the IPCC model to try and understand, if we implement best agricultural practices across the globe, how much could we increase soil organic carbon stocks from current? And on croplands, if we fully implement on all cropland everywhere, cover cropping, high residue returns, and low soil disturbance, so low tillage, sort of best management practices everywhere, we could maybe store around 15 petagrams of carbon total over time, which is equivalent to about 16 months of current emissions. And grasslands add another 14 months of emissions to that. Just to put an envelope on the absolute capacity for soils to do this, we have a rewilding scenario down the bottom left there, which is if we actually stopped agriculture entirely and let all ecosystems return to their native vegetation, how much could we actually get? And there we are. We only have about 3.3 years, 37 petagrams of carbon that we could add before we saturate this sink. So it's important to remember this is actually quite a limited sink. Some of the studies that you see showing large percentage impacts of soil organic carbon achieve this by focusing on the short term. So soil carbon stocks can go up quite rapidly at first when you implement a practice, but they reach a new steady state beyond which you have to continue your new practices in perpetuity in order to maintain the new status quo without getting any new stocks. And so I think it's a much better metric is to look at the total sink capacity, and it's quite modest. So if we're looking at soil organic carbon, we have to bear in mind that the size of the sink can't make much headway into current emissions, and it becomes maybe viable only within a deep cut decarbonisation where it can mop up some residual sinks from remaining sectors. It's also useful to remember, I think, always that we need to look at full life cycle terms at any practice we're looking at. And interestingly, when you look at soil carbon sequestration, it turns out that carbon sequestration is actually not its biggest impact even on greenhouse gases, and that its impact on nitrogen cycling and nitrous oxide emissions can actually overwhelm, especially when you take into account the energy cost of producing nitrogen fertilizers. So that's a massive factor. And any management that you put in place in order to increase soil organic carbon, if it increases yield, that frees up land elsewhere, and that has a leakage of impact that actually can be larger than the actual carbon that you store on site. And conversely, some practices, for example, if you put cover cropping into dry regions, they can compete for soil moisture. They can actually reduce your yields, and that can have a large negative consequence for leakage elsewhere, requiring new agricultural land to actually supply that same food you would have produced in that lane. So these kind of impacts are actually often overwhelm and dominate the actual overall balance of greenhouse gases from these soil carbon sequestration systems. A biochar, as I mentioned, is more stable than soil organic carbon. So we actually, if we convert to biochar, we can actually improve on that situation quite somewhat in terms of the sink capacity. This is a graph from a paper in preparation at the moment, but it's also closely related to an annex in the recent 2019 refinements to the IPCC greenhouse gas accounting practices, using available studies yet of the permanence of biochar to assess how much of it would be left over time if you add it to soils. The sink is not as permanent as, for example, sequestration in BECCS. We have up to around 80% of the carbon that you store with biochar would remain after 100 years, and ongoing emissions for that would have to be factored into any ongoing carbon accounting beyond that period. But it does allow us to, if we add biochar annually to soils, we can see in the right-hand graph here, the green, that returning biochar from crop residue into the soils allows a rapid increase in soil carbon stocks. And as long as you keep producing biochar and adding it, that more than compensates for any losses from decomposition into the long term. Interestingly, on the right-hand side, we can see that if we remove those same residues without returning biochar, that would deplete the native soil organic carbon, thereby driving land degradation and actually becoming a threat, particularly on already more degraded or vulnerable soils, to continued land use for agriculture on those soils. So we need to be very careful when we think about using residues as an input into BECCS or bioenergy systems, that we're not driving too much land degradation through doing that. If we return the biochar to the soil, it, in fact, through a process called priming, where it manages to reduce the turnover rate of the native soil organic carbon through adsorption onto its surfaces, it can actually you get a positive feedback whereby you actually increase native soil organic carbon stocks at the same time as adding biochar. So that's a win-win situation there. Biochar is often promoted as having benefits for crop yields. And while that's true, that's very context dependent. So if we look at field trials and pot trials that have been done, there's overall a large increase in yield on average, but there's some systematic bias in those trials in the sense that people tend to look at biochar trials in the context of soils that would benefit from them. So for example, highly weathered oxysoils and other soils which have more challenging soil properties for agriculture. There's more trials conducted on soils that actually see benefits. Overall, though, we can detect a trend and mechanistic drivers behind this, and we can see that biochar really drives an increase in crop yields where we've got more degraded, where we've got sandy or acid or less fertile soils, and has lower benefit, or if any benefit at all, on crop yields on soils that are already fertile and already have high carbon stocks. So if we want to try and put that into a context of how does that fit in against BECCS? This is a study from 2016 where produced a model with a large number of parameters to investigate the whole parameter space of where BECCS or biochar or pure bioenergy would be the most economically viable. And we can see in the graph on the right that the purple line, the biochar with bioenergy graph, is the highest on average around carbon prices ranging from about $400 or $500 per ton of carbon. Notice that's done dollars per ton of carbon rather than CO2. And BECCS coming in really around the $900 mark, actually becoming on average. But those error bars you see around those lines are very important in themselves. These are not so much uncertainties as variability depending on context. And some of the parameters that drive a lot of that variability are, for example, electricity price, crop yield impact of the biochar, which depends again on where you are and what soils you have there, carbon prices, which typically are expected to vary with time, and what discount rate you assume. So depending on where and when you are, there is a very broad range of carbon prices where any one of those three technologies may be the most viable one to think about. Even up to quite high carbon prices, we can have situations where BECCS is harder to implement, for example, in less developed countries with less access to capital. The biochar may become a viable substitute in those cases. It's probably worth spending just a minute to highlight the importance of discount rate there. In this study, we did look at quite a range from discount rates from around 1%. I forget what the top end was, maybe 8%. So the typical values that tend to be input into integrated assessment models are usually in the range of 4 to 5%, which results in integrated assessment models discounting future costs to such an extent that we see these results that we tend to prefer mitigation in the future and high carbon prices in the future over ambitious action now. And it's important to remember that these results that we see coming out of integrated assessment models are not actually predictions by the model per se. They have been input into the model in the form of a discount rate mathematically as a way of representing a philosophical or ethical stance that we prefer welfare now over the welfare of future generations. And there are others that have argued that there's no ethical reason that we should actually rate the welfare of current people more highly over future generations. That's a form of intergenerational theft, if you like, and that lower discount rates are better representative of how we should be thinking about these really long-term problems of climate change. And that it's thinking about the future is very different in this context to the kind of discount rates you might use in a project scenario where you're just thinking about return on investment over a few years within for a particular project. So the final slide with data on it I want to show you is from a recent study just published a week or so ago, where we conducted a large survey of US adults to try and assess what are the drivers of attitudes towards different types of different kinds of carbon removal strategies. And in order to do this, obviously, most people have not heard of, for example, BECCS, biochar, soil organic carbon, don't know much about it. So that we had an introductory blurb, which everyone got in order to give them some background information about each of these. These were carefully constructed to be non-biased towards one or the other, but just to be purely informational. And one of the most striking things that came out of this is that perceptions of naturalness really were one of the best predictors of support for a different technology. Now, stepping from the sort of policy into the politics side a little bit here, it's often said in politics that politics is the art of the possible, that the best policy may not be the ideal one that you would like to have, but the best policy is the one that you can actually get implemented in quite a in a world where there's very little disagreement over most things. Interestingly, within the US context in this survey, we saw that there was high support for more naturally perceived solutions, even among Republicans, as well as Democrats, although slightly higher among Democrats. But there was broad bipartisan support for wherever it was things were perceived to be more natural. So it may be easier to implement these kind of natural carbon solutions in terms of getting legislation through. So what does all this mean in terms of few policy take-homes? So for soil organic carbon, I think what we can take home from that is that there's a limited capacity in terms of the amount of carbon we can put into soils. It's quite inefficient in terms of how much carbon we store relative to the carbon we invest. It's also reversible. If we stop adding carbon, we will lose any additional stocks we've put in there, which means, for example, that we can't change our minds later on. If you want to invest in soil organic carbon, you need to be in it for the long haul. You can't later on decide to use those crop residues for BECCS without losing any of the soil organic carbon stocks that you originally built. However, so those are kind of the reasons you might not consider it, but on the plus side, the co-benefits for sustainable food systems are extraordinarily compelling, and that without managing carbon in soils, we will degrade our agricultural food systems to the point where not clear that we will be able to sustain a growing population of the world, which is already, as we've seen in some of the previous talks, quite a challenging issue. And also in terms of cost, soil organic carbon is a highly affordable solution, and where crop yields increase, if we focus on those kind of solutions, it can in fact have a negative cost. For biochar, some of the most important policy take-homes are firstly that it's much more efficient in terms of the carbon efficiency than soil organic carbon. That if we could combine biochar with carbon capture and storage of combustion CO2 and energy production and priming, that we can get a comparable level of carbon efficiency to BECCS. How easy and how economic it is to combine all of those elements together remains to be proven. It's somewhat permanent, but in the sense that it's got a much higher longevity than soil organic carbon, much less reversible than soil organic carbon, but it doesn't have the very long-term permanence that carbon CO2 sequestered in CCS does. Biochar, as with soil organic carbon, has important co-benefits for sustainable food systems. It's more expensive than soil organic carbon, but cheaper than BECCS. For BECCS, as we've seen, it's the most efficient in terms of a carbon removal strategy. It has the highest permanence, but it doesn't provide any of these other co-benefits towards food production, soils, soil conservation, and limiting soil degradation. And it's the most expensive option, so it requires much higher carbon prices to really drive it than some of these other options. And just to round it up with the final slide, just remember that optimal biomass use really depends on the context. So all of these different issues that I've raised here will play out differently at different places in the world and different times. BECCS may be where you've got a sustainable biomass supply chain from forestry, and you have the technological and capital investment available to do it in industrial nations. BECCS may well be the best option. But in other cases where you do not have the access to capital for the more expensive options, you do not have the industrialization, and supply chains are more problematic, we can think about these other options as being even more viable. We need to always think about how we value the co-benefits via sustainable food systems and biodiversity, and compared to climate change, but recognizing that climate change is itself a threat to food production and biodiversity. So that's, again, a difficult balancing act. And I don't think that the full analysis has been done to really answer those questions. We don't see things like soil organic carbon storage and biochar included in integrated assessment models. And I think we need to push more towards integrated assessments that include all the suite of options and look at their impacts, not just on climate mitigation, but all of these impacts, to really understand that. I don't think we're really at the point there where we can perfectly answer those questions. We need to think about the long term in any assessment, and we need to do full life cycle greenhouse gas accounting. I think another number of other people have also raised that. Overall, I think it's important to recognize that whatever types of carbon sinks and carbon drawdown we use, that we need to always push the message that these sinks are limited in how large they can be. There is a tendency, I think, at the moment to sometimes drive towards too much a reliance on carbon drawdown and allow emissions to rise. And we need to be clear in the policy world and in public-facing discussions that these are no substitute for mitigation.